Hi everyone, welcome back. We're going to focus on formal charges in this lesson. We're going to look at the charge distribution. A molecule might be neutral overall, but if it has certain areas of positive or negative charge that is, in a sense, built up on certain parts of the molecule, that can explain a lot of the reactivity and the properties. So let's start with this basic question here. Just looking at these two structures of carbon dioxide, do you think that they're both reasonable Lewis structures? Do they fit the octet rule? Do they look reasonable in terms of their bonding? Let's take a look at that. And if you look at all the valence electrons for this oxygen, 2, 4, 6, 8, carbon, 2, 4, 6, 8, oxygen, 2, 4, 6, 8, octet rule, everything's satisfied. If you look at this one over here, it looks different. But if you look at the octet rule, it actually is enforced in all of these cases. So 2, 4, 6, 8. So everything does have an octet here as well. However, you probably know from experience that we usually draw CO2 this way. It's not just the symmetry, but it's also experimental results. It turns out that CO bonds in carbon dioxide are equivalent. So they're shown to have the same bond length. Now, if you remember back to Gen Chem, single bonds, double bonds, and triple bonds have different length and therefore different strength of the bonds. So if you have two double bonds here, one on each side, and they're the same length, they're going to be the same strength approximately. Whereas here, you're going to see a difference between the strength of the bonds. This one will be weaker and this one would be stronger. And you'd have different lengths as well. So it turns out later we'll learn about resonance structures. These could be considered resonance structures of each other, meaning the molecule is really a combination or a hybrid of different resonance structures. But the one that makes the most sense usually for CO2 is to draw it this way based on how it behaves and what we know about it. One way to predict the Lewis structure that we should think about, so for example, why do we think of CO2 this way instead of this way? Is there a way we can figure that out without looking at the experimental evidence all the time? And one way to do that is to try to aim for the structure that gives us a formal charge of 0 on as many of the atoms as possible. So first, let's figure out how to calculate formal charge. It is the group number of that element in the molecule, and it is subtracting the number of bonds, or what I call sticks, and the number of dots, or unpaired electrons, or stones. So sticks and stones may break my bones. Do you ever know that? So one of my students taught me about this one. So it's easy to remember. Group number minus number of sticks minus the number of stones. Okay? So for example, with this structure, we're going to have some formal charges here. How do I know that? I know that because remember back in the last lesson, we talked about the honk rule and the valency. So hydrogen has 1 bond, oxygen 2, nitrogen 3, and carbon 4. 1, 2, 3, 4 bonds. Okay. When I see that, I know that those are the number of bonds for these elements to be neutral in the molecule. So let's look at just the honk rule and see, is the formal charge 0? So if you look at this oxygen right here, let's look at how many bonds it makes. 1, 2, 3. But we know oxygen prefers to make 2 bonds in order to be neutral or 0 formal charge. So therefore, I know this oxygen doesn't have 2 bonds, so it's going to have a charge. All right. So to calculate what that charge is, I'm going to use that equation. Oxygen is in group 6, so it's its group number or number of valence electrons it would normally have by itself. And then I'm going to sort of figure out, does it have more than 6 in general or less than 6 in general around it? And so to do that, I'm going to say 1, 2, 3 sticks and minus 1, 2 stones. And what you'll find out is that overall, oxygen by itself would feel like it's more neutral, but because of the way that it's bonded with this particular number of bonds and lone pairs, it actually has more of a +1 feel to it. So to indicate that, you want to write the charge. And I usually like to circle it just to show it emphasized so you don't miss it. Especially with negative charges, it's hard to see those sometimes. All right, so go ahead and determine first, are any of the remaining atoms have a formal charge that's not 0? You don't have to write 0 if it does. Then figure out the formal charge of the ones that are not 0. Go ahead and figure that out right now. Okay, we're back, and if you look at this carbon here, it actually would have a formal charge because it has not 4 bonds but something different. So 4 is the valence number minus 3 bonds or 3 sticks and 2 stones. So it's a -1 charge. So I put a negative by there. The rest of these do fit the honk rule, so they're neutral. So I'm not even going to bother calculating those. But you can go through the calculation and just see and verify that they will be 0. Now, the calculation does take time, and you don't want to be in a situation where you have to calculate every single atom in a molecule that doesn't fit the honk rule. So I would look at these patterns that are very common. When you look at a molecule and, for example, you see carbon with 3 bonds and no stones, no lone pairs, it's going to be positive. If you see carbon with 4 bonds in any of these configurations, it's going to be neutral. And if you see carbon with a lone pair and the 3 bonds, then now it's negative. It's got more electrons than it would by itself. So that means that you're going to have different patterns that you can recognize based on the number of bonds and the number of lone pairs. You can sort of start to recognize, oh, that's positive, that's negative, that's neutral. You want to be able to do that, not calculate every single time, okay? For nitrogen, how many bonds does it need to be neutral? Honk rule, H-O-N-C, right? H-O-N, 3 bonds, okay? So here are the different ways nitrogen can have 3 bonds. 3 single bonds, a double bond and a single, or a triple, okay? Don't forget the lone pair, that's very important. Now, if nitrogen makes an extra bond, so it uses the lone pair and makes a bond, what will the formal charge be? Well, you can calculate these. So 5 is the valence number, minus 4 bonds, and no stones, so +1. So all of these will have a +1 charge. Or think back to Gen Chem, and you know ammonium ion, NH4+. Well, there you go, okay? So let's put those positives in there. Now, when nitrogen makes does the other opposite thing, I have a typo here. I actually meant to put a lone pair here, not a hydrogen. The hydrogens were actually added by ChemDraw when I used it. ChemDraw thinks it knows what it should look like. So actually this is nitrogen with a lone pair here and a lone pair here and 2 bonds. Nitrogen with a lone pair here, here, and 2 bonds. So when nitrogen replaces a bond with a lone pair, now it feels like it's got more electrons. So this is going to turn out to be negatively charged. Again, use your calculation if you want just to verify that, but these are negatively charged. So what I want you to focus on is recognizing the patterns. Nitrogen with 3 bonds and a lone pair is neutral. Nitrogen with 4 bonds and no lone pair is positive. Nitrogen with 2 lone pairs and 2 bonds is negative. And you'll notice that some of these are more common that you're going to see, but you know, try to recognize these through experience. Okay, oxygen, honk rule says 2 bonds, H-O. So 2 bonds. You've got 2 lone pairs then to fit the octet rule. Over here then, we have something different. So it's going to be, let's figure it out, 6 minus 3 sticks and 2 stones, so +1. So if you notice there's a pattern, I put all of the positive ones on the left side of the page and all the negative ones on the right side of the page. Okay, it doesn't matter where you put the charge, just do it as close as you can. And over here you see you're going to have more electrons than normal. So when you see a lot of dots, you know, you tend to be more negative. And again, you can do the calculation, but an oxygen with 1 bond and many lone pairs to make the octet will be negative. And then over here, this is our neutral halogen. X represents our halogens, fluorine, chlorine, bromine, and iodine. Okay, so just know that symbol X is for those elements. So neutral there, and then here this is positive, and then here this is negative. And notice it's not bonded to anything here. This is like sodium chloride when it splits up into ions. You think of the ion by itself. All right, using these patterns, I would like you to practice looking at them and using them to answer these questions. And by the way, there's one typo, which is more information on this question in number 9 below. All right, go ahead and take a look at this, go back to here, go back and forth, and then figure out what you get. And then when you're done with that, go ahead and figure out, using the patterns, how do I know what the formal charge is here? And just to do one really quickly, carbon fits the honk rule, 4 bonds, so I know that's neutral. Oxygen needs 2 bonds, so that's neutral. But the nitrogen here would have a charge. It's got something other than 3 bonds. So I will go look at what does that nitrogen look like. That looks like this guy over here. So that means it's going to have a negative charge. If you get stuck on that, you can always fall back on your equation. Nitrogen is 5 valence minus sticks and stones, and you'll get -1. But I want you to use the chart as much as you can. By looking at it, you'll help to remember it better. Go ahead and work on 7 and 8 and 9, and then come back and we'll go through the answers, and then we'll do number 10. All right, guys, so we're looking at the answers now. So this oxygen I've identified be positive, this carbon is positive, this carbon is negative. Here I forgot to mention this carbon is where the lines meet, there's a carbon there. So you'll learn about that later, but if you didn't know that, there was a carbon there. Okay, so that's an oxygen here, it's negative, nitrogen is positive, and a bromine that's positive. All right, now there's something here in number 9 I want to point out. Carbon, if you look back to your chart, has a positive version and a negative version, but both with 3 bonds. The difference is the lone pair. So now most atoms, if you don't draw the lone pair, you are assumed to know that they're there. For example, right here in number 10, practice drawing in the lone pairs. Okay, so I know that there are lone pairs here because I know these have to have an octet. Oxygen has those, and carbon doesn't, already has an octet, and nitrogen needs 2, 4, 6, 8. So that's how I know how many lone pairs there are. Well, there's an exception up here, which is that there's one pattern that does not meet the octet rule. So find and circle it. Well, the one pattern that doesn't have it is this guy. It's the carbon that's a positive charge. Everything else does have an octet. So what I recommend, or what I want to emphasize to you, is that because carbon can have an octet or not have an octet, the only way for you to know which way it is if we always draw in the lone pair when it should be there and always leave it off when it shouldn't. So just like I was drawing in the lone pairs here, when you get to carbon and it doesn't have a lone pair, that means that it doesn't have one, okay? And when you see a carbon with a lone pair, it obviously has one then. So that's how I know whether to draw the lone pair or not. For carbon, it should already be there or not. For everything else, you don't have to show them, but I would show them, okay? I'm going to say that you need to show them because they're very important to know. So you just got to know that it looks like that, even though people don't write them in all the time, okay? So first I would go through these, draw in the lone pairs, and then practice again. See if you can figure out the formal charge without looking at your pattern sheet, okay? So maybe you still remember this one's -1, but can you figure out the other ones this time without the chart? So what you'll end up with is you'll end up with the same answers as above, okay? So go ahead and give that a try, and then practice the formal charge assignments and practice the Lewis structures that we've done so far. Practice your isomers, practice with the lone pairs. All right, see you next time.